I want to revisit problem 3, part B from the last section. We had a problem where we had 4 roots, and therefore we had a 4th degree polynomial, which is quartic. And I said that I would come back to the fact that you can have 2 roots that are the same. We'd seen it happen with quadratics. It happened when the parabola hit the x-axis in only one location. So I want to go look at the graph of this polynomial. So you will notice that it only hits the x-axis 3 times. So it's hitting here at -2. There's my +2, and there's my 3. But what I want you to notice is the shape of the graph at x equals -2. Notice that the graph bounces off, as opposed to passing through the x-axis like it does at the other 2 roots. When a graph bounces off or has a quadratic shape at a 0, we say that it has multiplicity 2. That means that at that root, it's actually squared, which is what happened when we did this problem, because as I said up here, those are my solutions. So my factors were x plus 2, x plus 2, x minus 2, and x minus 3. Well, we wouldn't write x plus 2, x plus 2. We would have actually written as x plus 2 squared, x minus 2, x minus 3. These multiplicities are going to tell you a little about the shape of the graph at that 0. So if you have a multiplicity 2, the shape of the graph at that 0 is going to be a parabola. Now, sometimes the parabola is opening up, sometimes it's opening down, but in either case, the graph seems to bounce off the x-axis. But if the multiplicity is just 1, the graph will pass through the x-axis at that point. So the way that multiplicities affect the graph of a polynomial, if you have a factor and n is 1, which means that you wouldn't see n, then the shape of the graph will appear to be linear. It'll look like it's kind of a straight line going through that 0. But if the multiplicity is 2, the shape of the graph will be quadratic. That means it'll look like a little parabola at that 0. If the multiplicity were 3, the shape of the graph would be cubic, or it would kind of look more like this at the 0. It will not look like that at the 0. In problem 4, we want to find the zeros of f of x is equal to x to the 4th minus 2x cubed minus 8x. We want to determine if there are any multiplicities and how the graph behaves at the zeros, which has to do with the multiplicities. I'm going to do this in 2 ways. I'm going to do the algebraic way, which is I'm going to factor out the greatest common factor first. I think I missed the fact that this should say squared. So I want you to notice that all 3 terms share a common factor of 2x's. So I'm going to take x squared away from all 3 terms. When I do that, the first term is left with 2x's, the second term is left with 1x, and the third term is left with no x's. Then the leftover trinomial can be factored by finding the 2 numbers that multiply to give you -8, but add to give you -2. Well, those 2 numbers are -6 and +4. So now if I apply the zero product property to the factored form, I get x squared is equal to 0, x minus 6 equals 0, and x plus 4 equals 0. So x must equal 0, x is equal to 6, and x is equal to -4. But there are only 3 zeros, and this was a 4th degree polynomial. That's because this was a multiplicity of 2. How do I know? Because it said x squared. That means that the shape of the graph at 0 should be quadratic. And these are my other 2 zeros. So my answers are really 0, 0, 6, and -4. Well, let's look at the graph instead. So let's say you didn't want to do it algebraically and you wanted to look at the graph. How would you determine this information from the graph? Here's the graph of x to the fourth minus 2x cubed minus 8x squared. So I see where it hits the graph. It hits at -2, it hits at 0, and it hits at 4. What I want you to notice is that the shape of the graph at 0 is a parabola. It doesn't pass through 0, it bounces off 0. That tells me by looking at the graph that it had to be a multiplicity of 2. So I know that x equals 0, so that's just x. It has to be squared. The other two zeros, the graph passes through the x-axis. Therefore, they're going to be linear factors, which is why I know the other two are x plus 2 and x minus 4. On your own, I would like you to find the zeros of f of x equals x cubed minus 4x squared plus 4x and determine any multiplicities. You can do it algebraically, or you can use the graphing calculator to help you out. If you don't have a graphing calculator, remember that you can always go to Desmos.com. When we started talking about polynomials, one of the things I mentioned was something called a turning point. If you read the graph from left to right, the graph is decreasing until you get to this point, because then it changes direction and it starts to increase until you get to this point. And the graph changes direction again and it decreases for the remainder of its life. These places where it changes direction have special names. They're called relative maximums or relative minimums. Now, what they're called depends on the textbook you're using. I've also seen them called local maximums and minimums. We can find the maximum and minimum values by graphing the polynomial on our graphing calculator and using the maximum and minimum functions. We've been introduced to this before, but we didn't do a lot with it, so we're going to really drive it home now how to use the maximum and minimum function on the graphing calculator. In problem 5, we want to look for the relative maximum and minimum of f of x is equal to x cubed plus 3x squared minus 24. So I want you to notice that when I graph this in the calculator, all I see is this. I see this, it's going up, and then it comes back down, and then it goes up again. So I can't see high or low enough on the graph. That means on my window, I want to change my window on how high and low I can see. That's the y maximum minimum. I had to play around with it for a little bit in order to see the highest and lowest points. So I ended up making my y minimum -50 and my y maximum 80. Again, I had to play around with it a little bit to get something that looked good. And then I got this. All right. So here's my relative maximum somewhere in the negative x values, and my relative minimum is somewhere around the positive x value, somewhere around like 2 or 3, somewhere in there. If you go and look at the table, remember second graph gets you to the table. If I go and look in the negative x direction, I'll notice that my biggest y value was 80 and it occurred at -4. So maybe -480 was my maximum. My minimum occurred in the positive x value, so then if I go back down, I'll see if I look at my y values, my smallest y value ended up occurring at -28. So maybe my minimum is at 2, -28. The other way of doing this problem is to use the maximum and minimum function, which is under second calc, or second trace. Second trace. Maximum is number 4 and minimum is number 3. So if I want to find this maximum, I would press number 4, and when it says left bound, I would move the cursor until I see it pop up over on the left side of my maximum somewhere. It doesn't really matter where, as long as it's to the left of the maximum, and then hit enter. Then you'll see at the bottom of the screen it says right bound. Move your cursor until it's over somewhere to the right of your maximum. When it says guess, just hit enter again, and then it'll tell you where the maximum occurs, and it turns out the maximum is at -480. To do the same thing for minimum, go back to second trace, but this time use number 3. I would move my cursor somewhere down over here so that it's to the left side of the minimum, and hit enter. When it says right bound, move the cursor somewhere over to the right-hand side of the minimum and hit enter. When it says guess, hit enter again, and it tells you, well, my calculator says 1.99999. You should know that's 2. So it really does tell me that the minimum is at 2, -28. You don't have to use the maximum minimum functions. We'll practice that more in class. What I would do is, for the purpose of this assignment, I would use the table, because if you're using Desmos.com, you'll probably want to use the table function. On your own, I'd like you to graph this function, f of x is equal to 3x cubed plus x squared minus 5x, and find the location of the maximum and minimum. Just use the table to help you out. I bet you thought you weren't going to see another application problem, but here it is. In problem 6, the length of a digital camera is 1.5 times the height. If the sum of the length, width, and height of the camera must be 6 inches, what dimensions maximize the volume of the camera? All right, so I don't actually know the length, the width, or the height. Here is a generic digital camera. It looks like a rectangular prism. Good to know, because we have length, width, and height. Okay, so now let's start with the part where it said the length of the camera is 1.5 times the height. So if we call the height h, then the length must be 1.5. I'm sorry, we call the height x. The length must be 1.5x. Here's the problem. They didn't tell me anything to find the width. So here's how it goes. They said that the sum of the length, the width, and the height is 6. Sum means add them all up. Well, if I want to know an expression to represent the width, how about I solve that equation for w? So 2.5x plus w is equal to 6, because I added my like terms. And then I'm going to subtract 2.5x. So now I know the width. I want to know what my length, width, and height are to maximize the volume of this camera. Volume of a rectangular prism is length times width times height. So the volume is going to be 1.5x times 6 minus 2.5x times x. I don't really want to multiply that out. That seems like a lot of work to me. The textbook does multiply this out. I claim to you, we don't even need to do that. What I'm going to do is I'm going to type that into my calculator exactly the way that I see it. So when y1 equals, I'm just going to put everything in parentheses, 1.5x, 6 minus 2.5x, and x. Then I'm going to graph it, and this is what I see. So because we're talking about a length, a width, and a height, you know that the answer has to be positive. We also said that we want to know the value of the dimensions that maximizes the volume. That means we're looking for a maximum. So let's use the maximum function on the calculator under second trace, number 4. When it says left bound, please put the cursor somewhere to the left of the maximum and hit enter. When it says right bound, move the cursor somewhere over to the right side of the maximum and hit enter. And when it says guess, hit enter again. Down at the bottom of the screen, it tells you that x is equal to approximately 1.6, and it tells you y is 7.68. This is the value of x that maximizes the volume of the camera. This is the maximum volume. So if x, which is my height, is 1.6, that means my height is 1.6, and it's in inches because the problem said that the sum of the length, width, and height had to be 6 inches. The length was 1.5 times x. So 1.5 times 1.6 is 2.4. So the length must be 2.4 inches. The width, we said, was 6 minus 2.5x. So the width, 6 minus 2.5 times 1.6, is going to be 2. So in order to maximize the volume of this camera, the height has to be 1.6 inches, the length has to be 2.4 inches, and the width has to be 2 inches. So the problem I want you to do on your own is I want you to do the previous problem again, except that the change you're going to make is that I want the sum of the length, width, and height to be at most 4 inches instead of 6 inches. And that's going to change your width, which is going to change your graph, which is going to change the maximum.